Great pleasure to introduce Daniil, who will be speaking on an introduction to vertex algebras.
So today I'll talk on vertex algebras. So plan is the first definition and example. Commutative. Vertex algebras. So then we'll talk about standard vertex algebras. So Heisenberg, Kac-Moody and Virasoro vertex algebras, and a definition of conformal vertex algebra. Then I'll have basic properties. Properties of vertex algebras and proofs. And finally, we'll talk about C2 and Schur algebra of vertex algebra. And here there will be no proofs at all. But I think for hour and 50 minutes it's more than enough. So let's start. First, I define field. So if V is a vector space and A, C is an element of two-sided. So this will be notation for two-sided series. So it's just sums AI, CI, where I is just integer, so it's not a ring, but something. It's a linear space. So we say that A of C is a field if for all B and A, C, B is actually a Laurent series. So it means that, okay, in this notation, ICI, AIE is 0 for I less than 0. So yeah, this is, I'll probably different notations for all this stuff. I'll follow Frankel's book and probably Frankel and Ben Smith. So so I'll have AC is sum AI C minus I minus 1. So almost all my objects will have sum of some index and degree minus 1. Almost all. So yeah, after I define field, define vertex algebra is following objects. So first E vector space, then vacuum vector. This is the notation. Then C translation operator, which is just an endomorphism of E, and something called state field correspondence, which is that okay, so notation will be A is a vector, and okay, and I have Y A Z some I and all. So it satisfies the following 5 axioms. Nothing interesting happens with vacuum vector. Second, if I apply field to vacuum vector, I get first term is A, the vector I start with, plus C times something else. So it's not Laurent series as required by definition of field, but it's Taylor series.
Is A an element of V or an operator? Is A a vector or an operator?
It's a vector.
Oh, I see.
Yeah. So yeah, I mean, yeah, I use different notation here, but yeah, I think in Frankel's book it's mostly A. A is vector and Y A Z is field, and these AIs are endomorphisms. Yeah, third axiom is that is about commutator of this translation operator and field. So the result should be derivative. Or if I apply T to vacuum, I got a theorem. Okay, maybe I'll sometimes sorry. I'll try to make the notation for vacuum vector really different from 0 number vector. And fifth is most advanced locality. So for any vectors A, B, there exists number n such that C minus W the n of commutator Y A Z and Y E W is 0. I take two fields and they don't compute, but they almost compute. Any questions? Okay. And almost all vertex algebras we consider will be graded, or even more precise, it's like C, they will be positively graded. So principle B is a graded vector space. Free of vacuum is 0. T is a linear map of degree -1, and this AN coefficient on Z minus N minus 1 is a endomorphism of degree A minus N minus 1.
How do you define the commutator for fields?
These are just I don't. These are Laurent series in two different variables. So the coefficient on each C to the I W J is A is like its usual commutator of two linear operators A minus I minus 1 and B minus 3 plus 1.
So there's no like normal.
No, not yet. I'll define it later. So yeah, now we just we can do anything because it efficient on every power of ZW is something very finite. Difference of two endomorphisms. Questions? Okay. So let's so the most basic example of vertex algebras is commutative vertex algebra, and so we should take V, a commutative algebra with derivation T, just the usual algebra with usual derivation, final Leibniz rule, and so I already get oh no. Okay, yes, so I already got vector space, vacuum vector, and translation operator. Translation operator is the C, and vacuum is 1. So I have to define fields, and fields will be Taylor series. So Y AZ applies to B is it's not necessary. Y AZ is sum Z to the n multiplication T n A, where n greater than 0, and over n factorial. So I just take this sum over with positive degrees. So I can write it as multiplication. Multiplication is right, left. Multiplication doesn't matter. It's commutative. Operator of multiplication. So I can write it like this: package all degrees of C into exponent. So if you what should I share? Field corresponding to 1 is identity just because T1 is 0. By applying this to 1, I get 8 plus something else, which is also satisfied. If I compute T, I get T times Tn A over n factorial B. Yes, so like the commutator is just T applied this expression. So I apply Leibniz rule, but so then next power of T here, and it's exactly what happens if I differentiate. It's also true. I've just said that T0 is 0, and locality is immediate because everything computes here, so I can take n equals 0. So I just have the commutator. It's 0. No multiplication. Everything just commutes. Yeah, so this is an example of vertex algebra.
What is the algebra? It's the set of all YAZ, the formal algebra.
Vertex algebra is for.
What are the elements of this algebra?
No, I take any I take any commutative algebra and produce you a vertex algebra. Elements of this vertex algebra are elements of algebra itself. So the corresponding vector space is the underlying vector space of an algebra.
So vertex algebra is not an algebra.
Yeah. Vertex algebra is it's So maybe it's not not very convenient name. So vertex algebra is not an algebra. It's just what I said. Bunch of fields and translation operator and a very convective.
Like some infinite dimensional Lie algebra, but it's also not a Lie algebra.
It's some kind of algebra, it's just not an associative algebra. It's like,
It's some kind of structure. Which we'll discuss in more details. It turns out that all these three properties that I said, first that two properties that the field is actually a Taylor series, not infinite series or not a Laurent series, so no negative terms at all. So it turns out that all these nice properties are equivalent and mean that your algebra is boring. So the following are equivalent. First, that YAC is endomorphism B Taylor series. Sorry, power series. It's power series. No negative terms. So just NV of Z for all A. Second, that for all AB, the field is just compute. So no power of E minus W necessary. And the third, that structure of vertex algebra on B comes from structure of commutative algebra on B, and C is a derivation. And C is derivation, and vector is Y, and so on. Try to write something too nice, then lost, you don't get anything new. It's proved in Frankel's. And for future reference, so the multiplication is in terms of fields is written as this usual associative operation, and in this case commutative, is A minus 1. So A minus 1 is something, is a constant term. So I multiply constant term, and so this similar formula will be used later. C2 algebra. Any questions? Okay, so this finishes the first part of our plan. Now we turn to Heisenberg and Kac-Moody.
Multiplication A minus 1. Why do you write A minus 1?
Was the field corresponding A is Y, AC is sum A phi C minus I minus 1. So for commutative, so this means that all your indices are negative. And first one is multiplication, and all the other ones are obtained by initiation.
sorry, so just to make sure I'm parsing that formula. So A minus 1 is an operator on
Yes.
V, is a vector in V, so that gives you the vector
Yes.
that corresponds to the product.
Yeah. I've just described you by linear equation ID goes to this. Okay. So let's now this. Virasoro will be a bit later because the construction is slightly different. Notation will be a bit different. So we'll start with Heisenberg and Kac-Moody, and we won't even discuss Heisenberg. We just notice that. Sorry, maybe Kac-Moody. The construction that we use is central extension of algebra of Laurent series in A. Frank uses Laurent's not Laurent polynomials, but Laurent series. It will be not very important for us right now, so we can use whatever. We consider central extension and this includes both Heisenberg. So if you take A is C with trivial bracket, it will give you Heisenberg, and if you take a simple algebra, it will give you affine Kac-Moody, untwisted affine Kac-Moody algebra. So all these examples can be described like this. So first I have to describe a vector space. So I have to start with vector space. Always. Somewhere should be kappa by invariant bilinear form on A, so that the bracket is let me write AN is equals AT to the N and hope that nobody gets confused. So AN is N plus N plus delta N plus N 0 kappa N delta N plus N 0 kappa A. This it has a highest weight, lowest weight, highest weight representation. So A of T direct sum. So let one central element. The basis of this algebra is this kind of thing, and one which is here. So volt 1. So A of T plus C volt 1 is a subalgebra inside in A hat. And moreover, it's a direct sum. So no, this term is always 0 if I take non-negative powers. So this is just a direct sum, and I can consider representation C, where A of T acts on this C by 0, and 1 acts by 1. So just a trivial the easiest non-trivial representation of this subalgebra, and I induce. And I say that this is my P kappa A. So this is induced representation of, so this is U of A hat, tensor U A T plus C. 1. This Yeah, so this is something that goes into negative powers of t. So only so it's a free module over u of t minus 1 a t. So starting with c, I get strictly negative powers of t. Yes, so this is my vector space, and so value is 1 test 1. Yes, so this will be a gradient vertex algebra. So I just say that degree of x Tn is minus n. So that I mean formally degree of multiplication by this operator. Degree is well defined. So it's just flipped degree here. It's well defined. So formally degree of a and 1 dot 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 a and a vacuum is minus n1 minus dot 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 minus na. And t is minus dt, which is also well defined. An is n a n plus 1 minus dt is minus n a plus 1, and it's well defined. So it will give us something well defined on this vector space. It's minus dt. And the remaining piece of most important one, state field correspondence. Where y let's start with elements of degree 1. There are Lie algebra of them, parameterized by these elements of Lie algebra. So y of a minus 1, 0 t is sum a k t minus k minus 1. So in this standard notation, yes, so this notation corresponds to standard notation. So AK, the endomorphism corresponding to probably A minus 1. K is a K in this sense. So no lines. And here by this element, I mean multiplication by this element. Yeah, any questions about what's happening? Okay. So now my next step is to define fields for higher. So y of a minus k 0, and so we will see. Yeah, so we will see later that apart from this episode 3 about commutator of t and y, we have later, so not proof that y of t a z means later in the Frankel's book. So y of t a z is also derivative of y of a z. Also give a derivative. And notice that a minus k0 is c k minus 1 over k minus 1 factorial of a minus 1. Thank you. Each application of t gives me next number, and exactly as taking derivative of negative powers of t, but I don't get this minus ones because I have minus dt. So at each step I get some. Yeah, so using these two pieces, we define this field as d dz minus 1 over a minus 1 factorial y a minus 1 0. And you can you write some explicit formula, but we won't anywhere binomial applications. Z minus a minus l minus. So yeah, the formula that we'll mainly use is this one with derivatives of initial field. Yes, and yeah, also this formula makes sense because so this one because we have to start with a minus 1 because of vacuum axiom that application to vacuum must give a minus 1 the same element. And to motivate all of the rest of this AKs and use this axiom about permutation relations with t. Coming to t, you must get derivatives. Yeah. Check here. This is the expression that satisfies this axiom. And yeah, so now we do normally ordered product. So okay, now I go back to the same notation for fields. So I c minus I minus 1, and let's positive terms and negative terms separately. So non-negative I give negative terms, and negative I give non-negative terms. And so I denote this as A minus, we denote this as A minus Z, and A plus Z. Yeah, so we divide field in parts, and the definition of field means that there are absolutely no restrictions on A plus, but A minus. So application of A minus to a vector should be polynomial t minus 1. And using this, I define normal ordered product of A and B as A plus C E of C. So nothing happens with positive terms, but negative we send to the right. And this is also because applied to vector, I get Laurent series, and I apply Taylor series. And here I get just the polynomial, and so I have finite amount of vectors, and I use definition of field for each of these vectors. So this is again a field. Questions? Okay. So now I use this knowledge to Okay, probably I should use my knowledge. In case of if we thought of this vector space as just a algebra, for example, take associated grade of graded of this U, then we would write something like y of AB x y a y. So we cannot do it now. So we have product. So instead of minus signs, I use negative x minus 1 k. Yes, normally ordered product of the corresponding fields. And let me also write the derivative. So I have to make sure I dot z minus n minus 1 over minus n minus 1 factorial by z. And for several fields, we order so normal ordering. So normal ordering is a non-associative operation. Matters. So I do it from left. Like all the closing brackets are on the right. This one. And yeah, it sounds silly, but it's like the only reasonable thing you can do. And yeah, I should rewrite it in even nicer terms. So in order to do it, let's it doesn't. So to not take this y everywhere we pass, we can choose bases. Say 1 dot dot t and define the corresponding so j I dot c is sum j I a t minus a minus 1. So this is exactly what I wrote here for the field corresponding to a minus 1. This is the field corresponding to corresponds to j I 0. Yeah, I also didn't tell. So here I so minus k here corresponds to n1 here, and so k minus 1 is minus n1 minus 1. Flipped sign. Yeah, so then you can rewrite this formula, and you can do it now in terms of basis. So for a basis element, j a1 and 1, we dot j and a 0, where you can, for example, can take lexicographic ordering on n's and then a's. So yeah, you get the same formula that I wrote, but without writing y's everywhere. So it's a normal ordered product of minus 1, factorial A1 Z dot ZZ minus NK minus 1 A1 minus NK minus 1 factorial J AK A. So this is a structure of vertex algebra on vacuum model over this A hat. Yeah, so let's when do we do break, like in 10 or in 15 minutes? Okay. So let's check the axioms. Oh, that I didn't erase, which is good. So yeah, I'll check and then erase them. It's not just once. Yeah, okay, so I give you 4 objects and I'm erasing it. One is spectrum. Don't do anything. 2 is definition plus induction. And yeah, so this is, for example, where this right order comes into play. So I apply normal ordering of AZ vacuum. So since A minus is on the right, it just disappears. So I get A plus C, vacuum. And since now like this B is nested normal ordering, then I can continue it and just get a product of the positive parts of these fields. And then I can telescope it back using this second property for these primary fields, which are Ji's. This plus J I vacuum is I multiply by something which is has non-negative index. I lose, so I should take a negative, so Z non-negative. G I minus 1 Q plus C times something. And this is exactly the element that I'm taking field of. So yeah, so this is and also nothing bad happens with derivatives. So this one is almost by definition on this corresponding to A minus K vacuum, and then it's some kind of have to check that if it's true for fields and it's true for their normal ordering. This one is just straightforward. And locality, so I will not prove the induction step. So so the induction step here in locality is as follows. So it's called BunG's lemma, and it's also in Frankel's book. If A, B, C are pairwise local, local meaning satisfies locality axiom, then normal ordering product of A, B, and C are also ununiform. So if you have, if your fields are obtained by normal ordering, then you have to check this only for primary fields, and you can also do something with T. So T is also some kind of induction. So the only thing that actually remains is to check the commutator relation for. Let me go back to A. So for sum A minus K minus 1 and sum L W minus L minus 1. So you have to do it once for these fields that start with, and here it's just a direct computation that sum A plus L Z minus K minus 1 W minus L minus 1. Okay. Plus these commutators that we should obtain by when K is minus L. So K kappa AV C minus A minus 1 W K minus 1. And here, if I have so if I say that so if I change the order of a sum, so if I say that K plus L is some U letter M, say that this is M, K remains, and now L is M minus K minus M minus 1 plus K. So this is exactly Z minus W to the power minus 1. Sorry, this is so the whole series. If I take all possible values of K, it's called delta function, delta of Z minus W times W to the minus M. And this is so now this is unit of delta function. So this A B delta prime C minus. So the end result is field corresponding to this telescope back to this M. So this telescopes back something in AB, and something times this delta, and something times delta prime, and both delta delta prime belong to the kernel of multiplication of Z minus W squared. So Z minus W squared times this is 0. So if you multiply delta function by the telescopes 0, and for delta prime you can grade by part and get so it telescopes again, double telescope. So this proves locality theorem, and also expressions like this, where you it's here. So what I've just computed is that for primary fields, G, A, C, W, GA, GB of W delta Z minus W plus alpha GA, GB delta prime Z minus W. And so this is closely connected to some operator product expansion. So if you write not commutator but product, then it's here will be 1 over Z minus W, here will be 1 over Z minus W square, plus something regular, plus something that does not use negative powers of minus W. Okay, so this is how Heisenberg and Kac-Moody vertex algebras work. So we have like this defining relation, then everything else questions. Yeah, so I think it makes sense to break it down. So yeah, maybe yeah, so I didn't prove to you that I get fields, but here it's free because of so if with graded vertex operator algebras, your fields are already with positively graded. Your fields are already Laurent series in endomorphisms, because if you take your n is too large, so your degree of z is too small, then this degree is also too small, and then you just don't. Sorry, it's not true. Definitely not. Yes, I just wrote one, and it's infinite actions. GI, but yeah, so you get for free that its application to any vector is Laurent series just because of degree reasons. That at some point you just get into negative degrees and then you are 0. So it's, or you can be an honest person and like compute this element GI with full average J's, and then you get 0 at some point, and it kills second vector, and very positive, very negative powers of Z correspond very positive J's, which are like annihilation operators, and they annihilate vacuum, and at some point you commute with everything and vacuum vector. That's what happens. Yeah, so yeah, let me maybe write properly what just happened. So delta of Z minus W is sum Ci W minus I minus 1. So this is some powers. Yeah, in any case, it's something that belongs to the kernel of multiplication of Z minus W, and it generates this kernel. So if I have Z minus W times something, let's just assume a two-sided series in both Z and W with coefficients in numbers situation, then my F is, oh yes, sorry. Maybe I should also write larger. So Z minus W times F CW is 0, then my W is some V of W times delta of C minus W. It's a GDIF I get from like coefficients, constant term in Z, and then I must have this delta of C W because of this reason. So it just tells me what happens on elements. So yeah, essentially I can only write expressions like this, and then delta prime and so on. Yeah, so that's what happens with Kac-Moody and Heisenberg. Well, for Heisenberg, this term is zeros, like just delta prime, but still, yeah. So this is out, and what we just did can be expressed as follows. So it's called. Let me formulate once. So we proved weak. There is also strong. Construction theorem, and it essentially says what I've just did. So if you have fields, if you have vector space V and homomorphism T, vector 0, vacuum, vector vacuum, and a collection of fields A alpha Z that satisfy some of the axioms of vertex algebra. So let's so commutator of C and A alpha C is alpha C prime, and that's almost everything. So T vacuum is 0, and A alpha C vacuum. So let's just denote the result by A alpha plus C times something else. So the requirement that it's a Taylor series, and we denote the first term by vector, we denote by A alpha. And we assume that let's assume we all don't write a product expression here. So big formulation is that if A alpha 1 minus n1, A alpha 2 minus n2, I'm writing homomorphisms corresponding I A alpha Z is the sum A alpha mi C minus n minus 1. If I have such fields, and if such vectors form a basis P, so I lexicographically order. So I take all the possible sequences of n1 dot and k, probably, and alpha 1 dot alpha k, where ni are strictly less than. Yeah, wrong chalk, thank you. Where ni is strictly less than 0. And in this case, the same formula that I wrote here, that y of this vector C is, well, you're the product of divided derivatives of oh yeah, exactly the same formula, but in this context, it is vertex algebra. Is the remaining missing piece of vertex algebra structure on So if I already have vacuum T and some generating fields, this condition, and also the condition that they are mutually local. Also here is in some set R mutually local. Yeah, so if I have some like initial set of mutually local fields, then I can generate everything using this derivatives and the normal order product. If this is description of my vector, so if this initial Fourier coefficients generate all my vector space. Yes, and there is a strong reconstruction theorem. So everything is the same, except vectors that I wrote span. We don't require them to be bases. So this formula may be not may be ambiguous. So it still defines vertex algebra structure. So still have vertex algebra structure, and it is unique with so it is a unique vertex algebra structure with this vacuum, this T, and y of A alpha is A alpha. I assume that to this vector corresponds this field, then I don't have any freedom. I must write promos like this. And they are well defined, even if I don't assume basis, even if I only assume span. Yeah, so weak reconstruction we kind of proved, strong reconstruction we will not prove. Questions? Okay, so this is what happens. Now let's discuss Virasoro algebra. Span and uniqueness. Here basis, here span, and here with existence, here existence and uniqueness. Virasoro vertex algebra. So let's start with Virasoro algebra. This is also a central extension of Witt algebra. So C, D, relations of C of zero. So this algebra is okay. There is again difference around polynomials and Laurent series. We will not care. So a basis here is Tn d over dt. Sorry, let me Cn plus 1 t. And we take the corresponding element here, Ln corresponds to this differential operator, and so here is 1, and permutation relation is Ln is, yeah, so if this minus sign, I get n minus n, Ln plus n, plus n plus n from n cubed minus n over 12 times central element. So this one is here, and the vector space we start with is a bit different. So now L minus 1 0 dot 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 F1 form sub-algebra. Yeah. So the only way we can get negative L is if you have -1 L -1, but it's zeros. This is a sub-algebra, and moreover, it's a direct sum of this and this, because any way to get not zero here is take n is 0 minus 1, and all of these options give this give 0 here. This is a sub-algebra, and similar to before, we can take the vector space C is the central charge number. We take vector space C where L minus 1, L0 does not act by 0 and 1 acts by C central charge. And now before VRC is induced representation, so it's Q of here, then the Q of 0, C. So as a vector space, it's as vector space. This is C of L minus 2, L minus 3. Similar to before, where we had vector space created by G, A, N with N less than -1. So also get free module over negative part. And now we have to find everything. So we start with degree. Degree of L minus N is minus N. So degree works slightly differently, like degree one piece is missing here, for example. And we define, so T is as before minus dt, which here can be realized just as action of L minus 1. And generating field. So now this minus dt turns L minus 2 to L minus 3 and so on, coefficients. So the only thing I have to do is to so yeah, so just move towards so using weak reconstruction theorem, it is enough to write a field y L minus 2. Sum of Ln z minus n minus 2. So this should be something of degree minus 2. And this is what I do. And I will not compute right the computation of data. It also can be done using relation of Lie algebra. So I'll just state the result that T of z and T of w is these derivatives of delta function, they depend on the variable. So the z and w variable differ by sign. I'm not doing it. my formulas may be wrong up to a sign. So I get third derivative of delta function of z minus w with central charge, and then something similar. So yeah, delta 3 primes comes delta prime t comes first, and t prime comes from choose which variable you differentiate. Questions? Yeah, so this gives me a structure of a vertex algebra on this vector space VRC. And this is called Virasoro vertex algebra. So I Virasoro vertex algebra is important because a lot of important vertex algebras are conformal. So conformal vertex algebra is vertex algebra plus omega conformal vector. So I write y of omega z as sum ln v is e minus n minus 2 with the following conditions that L and V as endomorphisms of V satisfy relations of Virasoro algebra, and L minus 1 V is T, and L0 V is grading operator. Multiplies elements of degree n by n. Yes, if you define what is a vertex algebra homomorphism, it will give you a vertex algebra homomorphism for C V, where C is that central charge that you compute relations. Questions? Okay, so now I will state and probably not prove in basic abstract properties of vertex algebras. Yeah, so it turns out that locality is a strong thing, and you can use it to. There are very strong consequences of this property, and so there is some notion of symmetry. So if you apply field A for B, it's almost the same as so e to the ct y minus c. Okay, so this is called skew symmetry. One of the consequences that you have this kind of symmetry, and also there is some kind of associativity in vertex algebras, which is stated as follows. So if let me write locality again. So C minus W n A y az y dw is z minus w m y w y az. Yeah, so let me apply both sides to some vector c. Now I use definition of a field, this expression, and I get that this is a Laurent series in W. This will be an element of V of Z of W. So I get a Laurent series in W, and its coefficients are Laurent series in Z. So I can get small, infinitely arbitrary small negative powers of Z, but my powers of W are bounded from below. But here it's in the other direction. So now I apply definition of field to this, and now this belongs to the same space, but with a different order of brackets. Sorry, and which I have the wrong number. So now my powers of Z are bounded from below. So if I look at this expression, so it must belong to the intersection. It means that the powers of Z and W are both bounded from below. So so it belongs to at the intersection of V, W, Z, and V, Z, W in the space that contains everything. E, Z minus 1, W, W minus 1. So it means that both your powers of Z and W are bounded. So the space that you get is it's like a Laurent series in both variables, and you can write it as a Taylor series localized in Z minus 1, W minus 1. But you also have to divide by Z minus Wn. So in the end, you get some element. So like a direct consequence of locality axiom is that y AC, y E W C, and y E W y A C C are expansions of the same element of what? This plus localized in Z minus W of B, C, W join C minus 1, W minus 1, C minus W minus 1 in the corresponding where they live, C, E, W, C, P, C, W, respectively. So this is kind of like a tautological reformulation of what happens in locality axiom. So this thing means that I get the same applied to any vector C, and having the same thing is that I go to some smaller ring, and I get the same result in both sides. So now the statement that you have to prove, and which we will not prove, is that so associativity means that it connects, so it's somehow connects expressions of type AK, L, C, which is brackets on the left. You apply first this, then this, and something of this form where your brackets are on the left. So you start from the left, so you get this like more and more endomorphisms, nested endomorphisms. Yeah, so the corresponding element is, so what I should write here is y of a c minus w e w c. So this is a field that I apply to vectors. I get a Laurent series in z minus w, and for each coefficient on this Laurent series, I take field again and apply it to C. So with nested construction, I can do it. It will be something well defined, so it should be. So this element should be expansion of this element that I get just by locality property in where it lives. And it lives in, I get some finite amount of powers of c minus w, but bounded powers of c minus w from below and unbounded powers of w. Yeah, so this is associativity property of W-algebras, that you have three expressions, and they are both they three of them correspond to the same element of this localized string, but expanded in like different rings of W and Z. So taking different expansions of W minus Z in like different regions. Okay, so I guess we're not proving it. So let me now. I should go. So I will use this to I'll write like this honest operator product expansion. We think that this is mean operator. Okay, maybe not like exactly mean, at least something that's called operator product expansion in Franklin's book. So something very close to what this is. So if I let me get it. I just write that y is y a c minus w, and this is some like actually finite expression if I end this off. So let me expand the inner brackets. I will expanding inner brackets. So y of a z minus w is sum a I z minus w minus I minus 1. Changing I to n, this will be y, and minus n minus 1. And this, so this has bounded from, so n is bounded from above. This is a definition of field that at some point I just start getting zero. I apply this ace to B. So at some point I just start getting zero, so my sum finishes at some point. So this is a Laurent polynomial with z minus w as promised, and you can write it explicitly. And this leads to, so maybe you have to rewrite it somehow, but this is almost as operator product expansion. So you collect all this non-regular term in this finite sum. So like the bad things happen at the near the diagonal, near diagonal z equals w. If you are computing things in like z and w separately, you are fine. But if you try to set z equal w, then your operations are not well defined. So this is how bad things are. Diagonal. This is some kind of formula. Yeah. Questions? Okay, so now we are almost ready to define C2 and Shu algebras. So yeah, these are the main constructions, like the main properties of vertex algebras, and you can do different things with them. So previous, yeah, frankly, this book does computation of explains computation of center of vertex of affine Kac-Moody algebras on critical level, using the corresponding vertex algebras on critical level, but we'll do different things. So let me just write one formula that is quickly follows from all this stuff. Not quickly, but it's if you want to compute a commutator of two Fourier coefficients, then you have this formula and yeah, where n is negative, then it's just product of n consecutive integers a and m plus a minus n. So it may not look very useful, but so good thing is that n is positive, so it's something corresponding to negative powers of z, and things corresponding to negative powers of z, they end soon. Some applications they end like at first or at second. It's you like cheap way to compute commutators. And we'll do one consequence of this almost immediately. So let's define C2 algebra of where C2, as I said, so this is as vector space. This is V over span of A minus 2, where A both belong to B. Take stuff corresponding to D in this product series that you get when applying fields to vectors. And it turns out that on representatives you can define multiplication. So A times B is A minus 1B. And I've erased this a long time ago, but it's the same formula that, so it's the constant coefficient on a field applied to vectors. So it's something that happened or in commutative vertex algebras with no quotients at all. You write such formula, it gives you a commutative associative product. If you write something like this in random vertex algebra, it will not give you anything good. But if you factor, then it's a well-defined associative commutative multiplication. So yeah, let me prove, for example, that this operation is well-defined on the right. I try to multiply A minus 1 minus 2C. I get something equivalent to 0, something that span. By interchange, I get 0 because it's b minus 2 applied to something. So it's I can change this to commutator, and then this formula becomes even better because I get something efficiency minus 3 and smaller. I get something minus 3 plus something minus 4, just because m here in this formula m is minus 1, minus 2, so it's already minus 3, and then it's smaller and smaller. So minus 3 is better than minus 2 because you can take TA. T shifts it's a formula that y c a c t c y and c yeah, so yeah, you can use these kinds of formulas to prove it's well-defined. So in order to check that this is associative or that it is well-defined, on the left we have to use Borch's identity, which I did not write. I probably will not write. And also check that this is a commutative product. It's essentially the same computation that I wrote. Subtract a minus 1 minus c from a minus 1 a minus 1 c, assuming associativity. Then it gives you commutator here, and in this formula you get something starting from minus 2, so something that is equivalent to 0 in this span. Yeah, so this is some kind of algebra, associative commutative algebra, even Poisson, which I also associated to vertex algebra, and you can often it's something reasonable. So there is it's finite dimensional, then vertex algebra has some nice properties. It's yeah, often it's not, but still you can say something. So for Kac-Moody algebra, it's jet scheme of algebra of no, it's just your algebra, just functions on your algebra. Yeah, you get jet scheme if you take associated graded filtration. There is such as construction, and now there is also definition of true algebra, where I assume that for C2 algebra, it's not necessary to assume that my algebra is politically graded or graded. So for Jou algebra, I will assume that my algebra is graded. So I define grade A sort sum I greater than 0, B A I minus 2. Oh, yeah, this is something that starts from A minus 2B and then goes. So I have the vector space V over span B sur P, and on this space I define operation on it executive. So A star B is something that starts with A minus 1B then goes in positive direction. So yeah, you can. So now it's harder to prove that this is a well-defined operation. So it will be associative. It will not be commutative. What do we need it for? It's for the following. So there is a notion of module over vertex algebra that I don't have time to define, but it's something that people are interested in. And so you have vertex algebra, positively graded. You have M module, also positively graded. So, plus graded. The action respects grading, will define action. So now I can take representative, like an element of this Joule algebra of A, and send it to action of top degree component A. Back A. So I take homogeneous element. I take this field. So I mean, a part of the definition of module is that I also have fields. So each element of my algebra A now gives endomorphisms of this module F. So I have such an endomorphism of M, and it turns out that it preserves graded components of M. Preserves graded pieces of M. And if you take the lowest degree piece, it will be M top directed. So, for some reason, in Arakawa's notes, the lowest degree piece is M top. So M top is representation of Joule algebra of A, and M top provides an projection between isomorphism classes of irreducible positive energy representations of P and simple modules over Joule algebra of P. So yeah, like if you want to study modules over vertex algebras, which are hard thing, then you can instead study, assuming properties, you can instead study modules over this Joule algebra of Phi. Yeah, so this is why it's useful, and how can you understand it? So, from grading on V, you get filtration on V just by taking first sum of graded pieces. 0 plus V1 plus dk dot plus dk is an increasing filtration on V. And just taking its image, you get filtration on this Joule algebra. And it turns out that associated graded is C2 algebra of V. I mean, it kind of makes sense. Sorry. There is a epimorphism from here to here, and in some cases, it's an isomorphism. Nice cases, like in nice cases, you can understand your Joule algebra better. Yeah, and it kind of makes sense that you get epimorphism from the C2 algebra because killing elements of lower degree just makes all the formulas boring. So if here you have elements of lower degree, you get just first term, which is written here, and here you also get first term, which is written. And the example of such thing is that Žu, kappa, A. I assume something should happen to kappa, like it should be non-degenerate or something. It will be U of A. And in this case, we say that V kappa A is parallelization. So if your true algebra is A, then V is called parallelization of. So here V kappa of A is parallelization of U of A. Yeah, so I'm not proving all of this, but this is an example of how such things may work. Yeah, that's all I wanted to say. Thank you.
Are there any questions for Daniil? Zoom.
What does C2 mean? Algebra.
Probably, I don't know, maybe just take.
Wait, there are CN algebra?
No, I don't think so. Maybe, I forgot. So, maybe there are, and they are less nice and.
What is the Jew of Virasoro?
I don't know. Good question. Narakawa sounds very strong in this, and then something super, like vector super algebra. So.
Elkanon said it's just a polynomial algebra, C of X.
Yeah.
Thank you. For no more questions, let's thank our speaker again.